Hey everyone, we are back and ready for Andrew and Dominic to talk about fundamental modeling concepts. They're going to present for about 20 minutes and then we'll do questions and answers after their presentation. So take it away, Andrew and Dominic.
How's it going? I am Andrew Chen. Been working on Kubernetes Docs for about 2 years now. So just to give you some context, I know some of you may have seen some of this material already before, but we want to give sort of an update and overview about the project that we've been working on. So to give some context, I met Dominic a while ago, and when he found out that I worked on the Kubernetes documentation, he started asking me all these questions, right? And I would kind of respond to him with like the stuff I'd read in the documentation, like what our standard thing was. But then upon like further questioning, like my answers kind of started like collapsing, and upon further scrutiny, like I couldn't give sufficient answers. So this led to like a phase where I started to question like, why is Kubernetes so difficult for people to understand, right? And went down this rabbit hole. And then Dominic showed me kind of like systems modeling, specifically fundamental modeling concepts, which he'll talk about a little later too. But like how he's used this in other projects to really help improve people's mental models and communicate. And so I realized we could really apply this to the Kubernetes documentation. So so for the past few months we've been working on this, and SAP has been very gracious in allowing Dominic to work on this for like a 6-month assignment. So, Dominic, without further ado.
Thank you. I got one.
Okay,
Thank
right.
you. So yeah, today I would like to talk about the fundamental modeling concepts in the context of the Kubernetes project and the Kubernetes documentation. And when we talk about modeling, that immediately begs the question, what is a model? And I'd like to want to motivate what is a model and what is modeling with two of my favorite quotes. One is, writing is nature's way to let you know how sloppy your thinking is. And the addition to that is, mathematics is nature's way to let you know how sloppy your writing is. And that is freely adopted so that the second quote reads, systems modeling is nature's way to let you know how sloppy your writing actually is. So when we come to the question, what is a model, right? A model is an abstraction of a system. A model is an abstraction of a system so that each and every fact about the model is a fact about the system. The opposite does not necessarily hold true. I can derive more facts from the system than I can from the model. In this case, for example, looking at the system, I could see its physical dimensions. I could measure its operating temperature boundaries. This is something that the model does not reflect. However, let me state this again. Each and every fact about the model is also a fact about the system. Now, the fundamental idea here is that two people will arrive at the same mental model whether they study the model or whether they study the system. And that also segues into a definition of what actually is a mental model. And here I use the definition as a mental model is simply the set of internalized facts, the set of facts that I have in my head about a system. Now, when we come to modeling, we immediately come to the question, what facts about the system do I want to include into the model? Now, there is no absolute answer to this question, and models form a hierarchy. Additional models add additional details. So in this case, for example, you see that the second model is a refinement of the first model, and it adds facts about the electric potential of the power source. And then the third model adds additional facts about the resistance of the light bulb. This actually leads nicely this actually enables us to clearly define the roles of novice, intermediate, and expert. So it shows that every fact that the novice knows is a fact that the intermediary knows and is a fact that the expert knows. Intermediates know more than novices, and the experts know more than the novice and the intermediary. However, there is a very important point to make, and that is that no fact that the intermediary knows contradicts or invalidates a fact that the novice knows. And the same is true for the experts. No fact the expert knows contradicts a fact that the intermediary knows or the novice knows. This sounds fairly straightforward and reasonable, yet I can point to a multitude of places in the documentation of Kubernetes where this is not true, where documentation targeted for the intermediate or the expert actually invalidates statements that were made before. So now the question, after knowing what a model is, why do we actually model, right? And this presentation focuses on one reason and one reason only. It is about communication. Sharing, or actually more accurately, transferring knowledge about a system. So to establish a baseline, we assume that if two people study the same system, they will arrive at the same mental model. And let us further assume that, for example, for Kubernetes, it takes me 3 months or 480 person hours to actually sufficiently understand the system. To transfer knowledge between people, the sender studies the system and creates a model for the recipient. The recipient then studies the model instead of the system. For the sake of the argument, let us assume that it takes me another 3 months to actually create a sufficiently accurate model of Kubernetes. But now it takes the recipient of the model only 1 month, 160 person hours, to study the model. Now there are only 2 participants in that, all right? We're in the negative. We actually lost 1 month here. But if we apply this to KubeCon, and we assume there are 4,000 participants in KubeCon, the accurate modeling would actually save 615 person years for 4,000 KubeCon visitors to accurately understand Kubernetes. So this actually shows how much multiplying force is in good documentation and is in good modeling. And of course, nothing ever comes easy, right? So there are some challenges. And the main challenge when it comes to modeling in the context of communication is about encoding loss and decoding loss. Encoding loss happening on the sender side, where I may not accurately describe what is actually happening inside Kubernetes, and decoding loss is on the sender side, on the receiver side, where the receiver did not accurately understand what I was trying to convey. Now, there are a few examples for challenges and problems. One, for example, misleading models. In Kubernetes, a great example for a misleading model is the notion of a declarative system and the desired state. So previously, I introduced that each fact about a model needs to be a fact about the system. This is the definition of a systems model. However, more than once, do we have situations where not each fact about the model is a fact about the system? There is a certain overlap, but you already have to know, you have to be an expert to know how far you can take this analogy. A very good example here is, for example, a train and a toy train. I can derive, for example, the physical appearance and the physical dimensions from the toy train of the actual train. If I want to take this any further, I cannot, right? Inspecting the toy train, I see that the toy train runs on little rubber wheels. Is the actual train running on rubber wheels? Of course it is not, and we all know that. But that is because we already know about trains. So these kind of models only work for you if you already know enough about Kubernetes so that you know you do not take it too far because the analogy breaks down in other places. When we come to the declarative state, or Kubernetes as a declarative system working towards a desired state, the by-the-book definition is that you start from a current state and the system will derive a set of coordinated, calculated actions that take you from the current state to the desired state. However, this is not how Kubernetes actually operates. Kubernetes operates one step of a time. It is a control system that at each point in its state graph determines the next action it's going to take until there are no more actions to take, and Kubernetes reached a steady state. Now, at a first glance, there is a considerable overlap between our definition of declarative system and the definition of a control system. However, if you take this too far, your mental model cannot explain, right, why you see certain behavior in Kubernetes, for example, if it comes to the replica set and already pre-existing labels. Other problems are, for example, misleading terminologies or inaccurate terminology. A great example in the context of Kubernetes is the term API server. So in the Kubernetes documentation, the active part is called the API server. The passive part is called the API server. And the totality of these parts is called the API server, which does not make it very easy or straightforward to talk about the individual parts. So one thing we did is that we, for our blog posts, adopted a different terminology, talking about the active parts of Kubernetes as the Kubernetes API, the passive parts of Kubernetes as the Kubernetes object store, and then the totality still as the API server. That also enables a clear refinement because especially the novice, and sometimes also bordering to the intermediary, ask how etcd actually fits into that. If you want to refine this model and then refine this terminology, it is actually fairly straightforward to explain how the etcd fits into the API server. Now, with everything we do, with the approach that we're trying to apply, we try to minimize encoding loss and decoding loss, and therefore increase the efficiency of the knowledge transfer between the sender and the receiver. So in summary, we basically aim for mental models that enable the reader to reason about Kubernetes. We aim for mental models that prevent the reader from drawing the wrong conclusions about Kubernetes by not knowing how far to take an analogy. And in general, we aim for a sound path from novice to intermediate to expert by adding one fact after the other without ever contradicting a previously made statement. And with that, I hand back to Andrew. Thank you.
Thanks, Dominic. So let me talk a little bit about our process, because let's see. So we've been writing blog posts, and this is sort of like a quick and dirty, MVP of like creating these different models. So we've been trying different topics, high availability or pods, Kubernetes API server, and that sort of thing, right? And to do that, we've had to we've been doing presentations to like sort of test out in SIG Docs, and we've also been doing interviews with engineers to help validate our models. So the idea is to like kind of build up a bunch of source material in the blog posts and get feedback and make sure like people understand it and like things are accurate. And once that is done, the plan is to then fold that back into the Kubernetes.io documentation, because we still need to decide exactly like to what level we want to integrate like these diagrams and stuff, because as been pointed out before, like some of them are more technical and you need to know about sort of like the language of modeling, but others are more straightforward, and you can just read it without knowing anything about FMC and still understand it. So that's what we're going to need to do, is kind of make these decisions of like what we need to add to the documentation and what needs to be more clear. And I think that's the work that we need to do in the coming year. Yeah. So we've interviewed like 4 engineers so far. And gotten some feedback and like try to validate parts of the models that we've done. And we plan to do more because obviously there's a lot more components to Kubernetes. No, because we've kind of been doing this as a discovery thing. Oh, so the question was, do we have a list of models that we're going through? So this is more of sort of like an organic discovery. So we've, as people like bring up topics and stuff, we've been modeling it. And that's kind of helped us to start figuring out like what are the important topics and what concepts are kind of still need to be filled out. So I think pretty soon we'll be able to have a more complete list, and then from that we can build like a doc plan in terms of like what needs to be changed in the conceptual section in Kubernetes.io. Right. So yeah, so this is a proof of concept, and then also just mapping out the space, like really understanding like what concepts are important to novice users. Yeah, so next steps are integrate the material into Kubernetes.io. So that's pretty much all I had, but is there any questions that people have about the project?
Let me just is that still on?
Yeah.
Let me just throw that into the room, so we can either do like a question answer, or we have about 10 minutes. We can also show you a concrete example of one of the components, the scheduler, that we model with this approach. I'm taking votes.
1 vote for the scheduler? 2 vote, third? Okay. Any objections? No? Okay, I guess we will do that.
Awesome, I love the scheduler. Let's do this. Give me just a second while I battle with technology.
Yeah, by the way, so the presentation that Dominic's about to go through, we're going to be giving this as an unconference at like 3 o'clock today, and I think room 605. So this is sort of a preview.
All right, so for the scheduler, this diagram depicts the high-level architecture of Kubernetes. So in this case, please note that the individual components, like controllers, scheduler, kubelet, they do not communicate directly, but they communicate indirectly via the Kubernetes API and the Kubernetes object store. So already from this high-level view, you can derive the guiding principle that Kubernetes, individual components of Kubernetes do not share state by communicating. They communicate by sharing state. Now, when it comes to the scheduler, obviously, the scheduler is tasked with pods and nodes. So the first question is, what is the typical sequence of events that we see in the context of the scheduler? And that is actually fairly simple to express. After a user or a controller creates a pod, the scheduler, monitoring the object store for unassigned pods, will assign this pod to a node. Subsequently, the kubelet, monitoring the object store for assigned pods, will execute this pod. So, in summary, mission statements reads, the Kubernetes scheduler assigns a pod to some node n. All right, but then the question arises, what does assigning actually mean, right? And diving deeper, the answer is also fairly straightforward. So this diagram depicts the Kubernetes objects that are of interest to the Kubernetes scheduler. Kubernetes represents a pod as a Kubernetes pod object, a node as a Kubernetes node object and the assignment of a pod to a node as a Kubernetes binding object. So we can define, equipped with this knowledge, that a pod is bound to a node N via the binding B. If and only if you can read the formula, the binding's name equals the pod's name, the binding's namespace equals the pod's namespace, and the binding's target's name equals the node's name. So, equipped with this knowledge, we may now formally define or formally describe the task of the scheduler as the Kubernetes scheduler for a pod P selects a node N and creates a binding B so that the binding predicate we just talked about, bound to pod to node via the binding B, yields true. So I got a pod object, I got a node object, and if there is a binding object that the predicate bound to holds true, that pod is scheduled to be executed on this node. Now this is actually a complete specification of what the scheduler does. We have about 12 lines of code that unambiguously state how the Kubernetes scheduler works. This is obviously not the implementation of the Kubernetes scheduler, which is fairly complex and large in volume. However, this is a complete specification of the behavior that you can observe when observing the Kubernetes scheduler. So the Kubernetes scheduler, in an infinite loop, waits for and checks for pods that are not bound. If there is a node name specified for the pod, which basically means that somebody manually scheduled this pod, then the Kubernetes scheduler will schedule this pod on this node, no further questions asked. If this node name is not set, the Kubernetes scheduler will select a node, and if it finds a suitable node, it will then create a binding object between the pod and this node. So graphically represented, fairly straightforward. Node name is not empty, use this node. Node name is empty, select a node. If you can't find one, start all over again, and if you found one, create the binding. So that already hints to the fact, since this loop is actually fairly straightforward and not very complex, this points to the fact that the selection of the node is where the complexity of the scheduler is actually buried. Now, selecting a node for a pod is a two-step process. First, the scheduler selects a subset of nodes that are qualified to host the pod, right? And then second, the scheduler selects a node from this subset that has the highest ranking or the highest priority for this pod. How does this look like? Well, we have a set of filter functions to actually select the qualified nodes. So you can think of the filter function as a conjunction of a set of filter functions that are implemented in the scheduler. One example for a filter function is a basic sanity check, all right? Does the node pass basic checks? In that case, we look at the attributes of the node object, like, for example, the unschedulable flag better be not set. The node phase shall be running, and there should be a node condition, the node condition ready equals true. Only then will this node be considered eligible to run this pod. Once again, the formula is actually straightforward on this filter. The implementation details of this are no question asked. The implementation details are fairly complex. On a specification level, this is it. All right, there is no much more to it, to the basic sanity check. Now we got other checks, like, for example, taints and tolerations. Who doesn't like taints and tolerations once it comes to nodes and pods? Surprisingly, actually, taints and tolerations are fairly straightforward. The object model behind it is not even that complex, and the statement is also a fairly simple one. The scheduler may assign a pod P to a node N if and only if for each taint that is an element of the node's taints, there must be a toleration that is an element of the pod's tolerations so that the toleration matches the taint. Done. This is the entire specification of taints and tolerations. Again, the implementation in the scheduler in source code is actually fairly complex, right? But the specification on a specification level, this is it. If we come to affinity or anti-affinity, I personally was surprised that the object model behind that is way more complex than behind taints and tolerations, and so are the formulas, so I only go over them on the highest level. The scheduler may assign a pod P to a node N if and only if the node affinity, pod affinity, and pod anti-affinity all hold true. For the node affinity, for example, a pod must be assigned to a node such that the node's label matches the pod's node affinity requirements. The same can be said about the pod affinity. The same can be said about the pod anti-affinity. I spare you that. And we go straight to the rating functions. Rating functions are just the same. We run the pod and the node through rating functions. We sum them up, right? And we select a node from the highest rated ones. I would say it's enough graphs, it's enough math. I'm pretty sure you all get the gist. They basically look like the filter functions. And we, hold on, I lost my preview. Yeah, here we go. They look like the filter functions, and we go right into a very quick case study for the scheduler. So we have a cluster, and in this cluster we have a few nodes without a GPU, and we have some nodes with a GPU. We have some pods that require the GPU, and we have some pods that do not require the GPU. So the mission statement is fairly straightforward. For each pod that does not require the GPU, run it on a node without the GPU, and for each pod that requires the GPU, run it on a node with the GPU. So what are we going to do first? First, in this case, there are many possibilities, but this is the way that we are going down to now. We add a taint to the nodes, and with this taint, immediately none of the pods is eligible to run on this node, right? That's why for the pods that require the GPU, we need to give them a toleration so that they tolerate this taint. However, now that only states that the pods can run on this node, but it doesn't say that the pods must run on this node. For this, we need to get a step further, and we add some labels to the nodes, which will not change the possible assignments at this moment, but then we give we give the pods a node affinity, and then with the node affinity, we actually split the set of nodes and the set of pods just according to our specifications, where the pods not requiring GPU run only on nodes without the GPU, and the pods requiring GPU only run on nodes with the GPU. And I do believe, yes, with that, we actually sped through this presentation as well. Thank you very much. Oh, thank you, thank you. And now we open up for questions.
I have a question. Is there any chance that Yeah, so I have a question. In the future, would we potentially open this up to focusing on when the scheduler starts evicting pods, kind of that secondary step of if a pod becomes unschedulable for whatever reason, kind of that after they're running, then what's the life cycle like ongoing?
Yes, this is actually a very good one, and it fits nicely into the story of modeling and how models are a refinement, right? You saw that, for example, on the very first slide, right, where we look at the control loop at the highest level, right? This, and I said it defines the control loop in its totality, right? If we now want to go a step deeper, we need to look into select. But you are right, that is not just a refinement. There are also aspect models, right, where you say, all right, Now, you understand what the pod is, you understand what the scheduler is, you know what taints and tolerations are, what node affinity, anti-affinity is. But now let me tell you also about the possibility of the controller to evict nodes. So that, to evict pods. So then you would actually add, right, other commands that the scheduler can issue. Right now, we modeled the scheduler so that it can only issue one command, that is create. All it does in this model is it creates a binding, right? Once you come into, and now let me tell you more about the scheduler, right? Then you enhance the command surface of the scheduler and say, and now this is where the scheduler can actually start to evict pods, right? So you add facts to the model. You can do that horizontally, you can do that vertically, right? But the most important one is you never contradict the previously made statement. Right? You just add more detail, right? And me as a novice, I may not know about the fact that the scheduler can evict, right? But you know. But by me learning that the scheduler can evict, I only increase my knowledge, right? But I do not have to shed any previous knowledge that I gained so far.
Any other questions?
Just, can you send me the link to both of these so I can include them in the notes?
Sure.
Great, thanks.
And then one thing I should have mentioned earlier is I would say the high-level purpose of this project is to sort of be a Rosetta Stone so that we all understand Kubernetes better, and then we can be much more authoritative when we write about it. So, because I think that was, one of the areas that I was concerned about. Like, I personally felt that I didn't quite understand Kubernetes deep enough to write things and be confident that they were correct. So my hope is that this will, put everyone on the same page and then empower us to write, better documentation that is clear and concise and correct.
And let me state one more thing, why I said this is one of my favorites, right? The Kubernetes scheduler, the implementation of it is very complex. It has like many, many thousand lines of source code, right? But it is sufficiently described with a 12-line specification, right? That basically in all areas of your Kubernetes journey, whether you're a beginner, a novice, or an expert, that you can understand, and that will help you to build an actual sufficient mental model and lift the curtain of magic, right, behind a single component, in that case, the scheduler.
Thank you very much.